the same, this is bigger, it's because this second factor is bigger than this that you actually get that n squared feel, that slowness to the algorithm. Well, let's just see this another way rather than just based on buckets. We can express this actually completely formulaically, very simple formulas. So recall our implementation of this was just this algorithm. We have a base case at the top. Then we've got some recursion going on, sort the left, sort the right, and then merge. So let's now slap some running times on this. And here's another takeaway. You don't even need to write or see code in order to analyze the running time of an algorithm. We can just kind of infer it from the pseudocode. So I claim that the running time of this algorithm, call it t for time, given an input of size n, is going to be 0 if n is less than 2. In other words, it takes me no time at all to sort a list of size n if n is actually less than 2, if it's 0 or 1, right? It's just done. So we'll claim the cost of that is 0. Well, that's obviously not the running time of merge sort. It's not 0. There's got to be some approximation of n log n. So let's get there. So what's the recursive case? Well, that was the base case. So in the recursive case, what's the time involved to sort n elements? Well, here's where we can kind of cheat with ourselves and just say, it's this plus this. The running time to sort n elements equals the running time to sort n over 2 elements, plus the running time to sort n over 2 elements, left half plus right half, plus the n is the merging. So again, a quick sanity check here. If the very first step of the algorithm is sort the left half, sort the right half, here's the left half, here's the right half, merging, how do you merge? Well, think about what Joseph was doing. If I kind of do it with my fingers here, he was pointing to the left end of the left half and the right end of the right half. And the left end of the right half. And what was he doing? He was comparing them, figuring out which is smaller. Then he decided one is smaller, so he'll pick that one out of the lineup. Then what did he do with this finger? He advanced it to the next leftmost element of the left half. What did he do next? Well, in this here, here, then he would go here, here, here. So think about how many times did my fingers move from left to right? Well, once per bucket. Right? I only moved to the left. I never did this. Casey did a lot of this last week, going back and forth, back and forth. Joseph never did that. So where do we get this n factor? You sort the left half. You sort the right half. Then you just essentially, conceptually, have to point at each bucket once in order to move it into place, as Joseph did. So unfortunately, this isn't the answer. I don't even see a log n in here, because now we have to recursively answer our same question. What's the running time involved in sorting n over 2 elements? Well, what's it going to be mentally? Well, it's going to be t of n over 4 plus t of n over 4 plus n over 2. But this is just going to get very messy very quickly. So let's try to simplify this with just an example. So that is, in fact, an algorithm. It's a recursive formula, rather. Let's try to do this with actual numbers. Suppose, for the sake of discussion, we've now got 16 buckets, 16 numbers, just so the math is a little more compelling than 8. What's the running time to sort, using this algorithm, 16 elements? Well, it's t of 8 plus t of 8, otherwise known as 2 times t of 8, plus 16. So to be clear, one of those t of 8s is the amount of time involved to sorting 8 elements on the left. The other t of 8 is 8 elements on the right, assuming a total of 16. And what's the 16 for? Merging those, right? Taking 8 from both halves, merging them together so that you get a collectively merged 16 elements. So now we have to dive in. And let's do this one because it's relatively easy numerically. What's t of 8? Well, t of 8 is just 2 times t of 4 plus 8. What's t of 4? T of 4 is 2 times t of 2 plus 4. What's t of 2? T of 2 is 2 times t of 1 plus 2. Right, I'm just having. So hopefully this is going to bottom out. And sure enough, what's t of 1? If I hand you a list of size 1 and I say sort this, just as Joseph did, you hand it right back. You're done. So now what can we do? Just algebraically, we can say, all right, well, I've got this t of 1 here. Well, I can plug this in here. So this 0 is going to go here. That's going to give me 2 times 0, which is 0, plus 2 is 2. So now I know what t of 2 is. So now I can plug that 2 in there. So 2 times 2 is 4. 4 plus 4 is 8. So that means this thing is 8. So let's change this. So 2 times 8, that's 16 plus 8, right, is, come on, so I'm the only one doing it, 24. And if we keep going with this, what should we get in the end? 64. All right, so 64, quick sanity check then. So I claim that this algorithm runs in n times log n. So I claim that that's going to be 16 times log base 2 of 16. Well, for those who remember, what's this? It's 4, right? So log base 2 of 16 is 4. 16 times 4, 32. 64. So sure enough, this is frankly proof by example, which is an illegitimate way of proving any point that you ever might need to make academically. However, it at least confirms, albeit with one simple example, that we are getting numbers along the lines of n log n. And even though, again, this is just one simple example, recall just what the implications are when you actually run this. If I go again to this tier, let's choose reversed. So now this is the worst possible scenario for all of these algorithms. Merge, sort, recall is on the bottom left here. Let's see just how well it performs in this potentially worst case scenario. Last time, recall, we started with random. So those other performers, heap, quick, shell, those are still looking pretty good. Merge, sort's pretty good. So we chose a decent one. Insertion, sort, which we didn't talk about, it's a little slower. But my God, bubble sort and selection sort are going to be here all day with these examples. So that is, in fact, n log n. So it's one thing to see these things graphically and to kind of reason through them. But something one person did on the internet, which is actually quite fascinating, is actually assigned audible frequencies to the lengths of these bars so that you can actually hear these various sorting algorithms. This is about a minute of audible animation. Let me go ahead and pull this to the forefront. This is insertion sort. This is bubble sort. But again, sound aside, notice that bubble sort, true to its name, the big values are kind of bubbling up to the top. Slowly, but bubbling up to the top. Selection sort. And again, remember, selection sort keeps plucking the smallest element, so it makes sense that it's looking correct on the left, but not yet the right. Merge sort, where you can really see the halves that Joseph was merging. This is something called gnome sort. So that's it. This is n log n. This is CS50. We will see you on Wednesday.